DEFLATE from Wikipedia, the free encyclopedia. DEFLATE redirects here for other uses. See DEFLATE disambiguation. This article needs additional citations for verification. Please help improve the article by adding citations to reliable resources. Unsourced material may be challenged and removed. Find sources DEFLATE-news, newspapers, books, Scholar, JSTOR, JSTOR, January 2009. Learn how and when to remove this template message. In computing, DEFLATE is a lossless data compression file format that uses a combination of LZSS and Huffman coding. It was designed by Phil Katz for version 2 of his PK-zip archiving tool. DEFLATE was later specified in RFC 1951-1996. Katz also designed the original algorithm used to construct DEFLATE streams. This algorithm was patented as U.S. Patent 5,051,745 and assigned to PK-Ware Incorporated. As stated in RFC document, an algorithm producing DEFLATE files was widely thought to be implementable in a manner not covered by patents. This led to its widespread use, for example, in gzip compressed files and PNG image files. In addition to the zip file format, which Katz originally designed, the patent since expired. Contents. 1. Stream format 1.1, duplicate string elimination 1.2, bit reduction 2, encoder/compressor 2.1, deflate 64/enhanced deflate 3, using deflate in new software 3.1, encoder implementations 3.2, hardware encoders 4, decoder/decompressor 4.1, inflate only implementations 4.2, hardware decoders 5, see also 6, references 7, external links. Stream format. A deflate stream consists of a series of blocks. Each block is preceded by a 3-bit header. First bit, last block in stream marker. Bullet point 1, this is the last block in the stream. Bullet point 0, there are more blocks to process after this one. Okay, hold on. Second and third bits, encoding method used for this block type. And so we have 2 bits grouped together. 0, 0, a stored, aka raw or literal section between 0 and 65,535 bytes in length. 0, 1, a static Huffman compressed block using a pre-agreed Huffman tree defined in the RFC. 1, 0, a compressed block complete with Huffman table supplied. And 1, 1, reserved, don't use. So that could be an error if you see a 1 and a 1. The stored block option adds minimal overhead and is used for data that is incompressible. The stored block option adds minimal overhead and is used for data that is incompressible. Most compressible data will end up being encoded using method 1, 0, the dynamic Huffman encoding, which produces an optimized Huffman tree customized for each block of data individually. Instructions to generate the necessary Huffman tree immediately follow the block header. The static Huffman option is used for short messages where the fixed saving gained by omitting the tree outweighs the percentage compression loss due to using a non-optimal, thus not technically Huffman code. Compression is achieved through 2 steps. Bullet point, the matching and replacement of duplicate strings with pointers. Bullet point, replacing symbols with new weighted symbols based on frequency of use. Duplicate string elimination. Main articles LZ77 and LZ78 and LZSS. Within compressed blocks, if a duplicated series of bytes is spotted, a repeated string, then a back reference is inserted, linking to the previous location of that identical string instead. An encoded match to an earlier string consists of an 8-bit length, 3 to 258 bytes, and a 15-bit distance, 1 to 32,768 bytes, to the beginning of the duplicate. Relative back references can be made across any number of blocks as long as the distance appear within the last 32 KIB of uncompressed data and decoded, termed the sliding window. If the distance is less than the length, the duplicate overlaps itself, indicating repetition. For example, a run of 10 identical bytes can be encoded as 1 byte followed by a duplicate of length 9, beginning with the previous byte. Searching the preceding text for duplicate substrings is the most computationally expensive part of the DEFLATE algorithm and the operation which compression level settings affect. Bit reduction. Main article, Huffman coding. The second compression stage consists of replacing commonly used symbols with shorter representations and less commonly used symbols with longer representations. The method used is Huffman coding, which creates an unprefixed tree of non-overlapping values where the length of each sequence is inversely proportional to the logarithm of the probability of that symbol needing to be encoded. The more likely it is that the symbol has to be encoded, the shorter its bit sequence will be. A tree is created containing space for 288 symbols. 0 to 255 represents the literal bytes / symbols 0 to 255. 256, end of block, stop processing if last block, otherwise start processing next block. 257 to 258 combined with extra bits, a matched length of 3 to 258 bytes. Bullet point 286, 287, not used, reserved, and illegal, but still part of the tree. A match length code will always be followed by a distance code. Based on the distance code read, further extra bits may be read in order to produce the final distance. The distance tree contains space for 32 symbols. 0 to 3, distances 1 to 4. 4 to 5, distances 5 to 8. 1 extra bit. 6 to 7, distances 9 through 16, 2 extra bits. 8 through 9, distances 17 to 32, 3 extra bits. Bullet point ... 26 to 27, distances 8,193 to 16,884, 12 extra bits. 28 to 29, distances 16,385 to 32,768, 13 extra bits. 30 to 31, not used, reserved, and illegal, but still part of the tree. Note that for the matched distance symbols 2 to 29, the number of extra bits can be calculated as n over 2, all minused by 1. The two codes, the 288 symbol length / little tree, is the 32 symbol distance tree, are themselves encoded as canonical Huffman codes by giving the length of the code for each symbol. The bit lengths are themselves run length encoded to produce as compact a representation as possible. As an alternative to including the tree representation, the static tree option provides standard fixed Huffman trees. The compressed size using each of these static trees can be computed using the same statistics, the number of times each symbol appears, as are used to generate the dynamic trees. So it's easy for a compressor to choose whichever is smaller. All right. Encoder / compressor. During the compression stage, it is the encoder that chooses the amount of time spent looking for matching strings. The glib/gzip reference implementation allows the user to select from a sliding scale of likely resulting compression level versus speed of encoding. Options range from 0, do not attempt compression, just store uncompressed, to 9, representing the maximum capability of the reference implementation in zlib/gzip. Other DEFLATE encoders have been produced, all of which also produce a compatible bit stream capable of being compressed by any existing decoder. Differing implementations will likely produce variations on the final encoded bit stream produced. The focus with non-zlib versions of an encoder has normally been to produce a more efficiently compressed and smaller encoded stream. DEFLATE 64 / enhanced DEFLATE. DEFLATE 64 specified by pkware, is a proprietary variant of DEFLATE. It's fundamentally the same algorithm. What has changed is the increase in dictionary size from 32 KB to 64 KB, and extension of the distance codes to 16 bits so that they may address a range of 64 KB in the length code, which is extended to 16 bits so that it may define lengths of 3 to 65,538 bytes. This leads to DEFLATE 64 having a longer compression time and potentially a slightly higher compression ratio than DEFLATE. Several free and/or open source projects support DEFLATE 64, such as 7-zip, while others, such as zlib, do not, as a result of the proprietary nature of the procedure and the very modest performance increase over DEFLATE. So that sounds like patent trolling to me, like, oh, hey, we have this algorithm that uses 32 bits. Oh, let's just do it with 64. Oh, look how smart and original we are. I have some choice words for people like that. Using DEFLATE in new software. Implementations of DEFLATE are freely available in many languages. C programs typically use the zlib library, licensed under the zlib license, which allows use for both free and proprietary software. Programs written using Bordlin dialects or Pascal can use PassZlib, a C++ library, is included as part of 7-zip/advanced COMP. Java includes support as part of the standard library in java.util.zip. Microsoft.NET Framework 2.0 base class library supports it in system.io.compression namespace. Programs in Ada can use zip-ada, peer, or zlib-ada, thick binding to zlib. Encoder implementations. pkzip, the first implementation, originally done by Phil Katz, is part of pkzip. Zlib/gzip, standard reference implementation used in a huge amount of software, owing to public availability of the source code and a license allowing inclusion into other software. Crypto++ contains a public domain implementation in C++ aimed mainly at reducing potential security vulnerabilities. The author, WEIDAI, states, "This code is less clever, but hopefully more understandable and maintainable than zlib." So I might want to look at Crypto++ because I am a fan of less clever code. Bullet point, 7-zip/advanced COMP, written by Igor Pavlov in C++. This version is freely licensed and tends to achieve higher compression than zlib at the expense of CPU usage. Has an option to use DEFLATE 64 storage format. Okay. We're on PuTTY. PuTTY, within quotes, sshzlib.c, a standalone implementation capable of full decode but static tree-only creation by Simon Tatham, MIT license. Plan 9 from Bell Labs Operating Systems libflate implements DEFLATE compression. Hyperback uses its own proprietary lossless compression library written in C++ and assembly with an option to implement DEFLATE 64 storage format. ZOPFLI C implementation by Google that achieves highest compression at the expense of CPU usage. ZOPFLI PNG is a variation of ZOPFLI for use with PNGs, Apache licensed. IGZip, an encoder written in x86 assembly, released by Intel under the MIT license, 3x faster than zlib-1, useful for compressing genomic data. Advanced COMP uses the higher compression ratio version of DEFLATE as implemented by 7-zip, or optionally ZOPFLI in recent versions, to enable recompression of gzip, PNG, MNG, and zip files with the possibility of archiving smaller file sizes than zlib is able to at maximum settings. Okay, we're on section hardware encoders. AHA361-PCIX /AHA362-PCIX from Comtech AHA Comtech produces a PCI-X card within parentheses PCI-ID colon 193F colon 0001, capable of compressing streams using deflate at a rate of up to 3.0 gbit /s, so gigabits, and then within quotations 375 megabytes per second for incoming uncompressed data, accompanying the Linux kernel driver for the AHA361-PCIX is an, within quotes, AHA gzip, end quote, utility and customize, within quotes, mod_deflate _AHA, end quote, capable of using the hardware compression from Apache. The hardware is based on a XILINX. There might be two L's, there might be one, I'm not sure. Vertex FPGA and 4 custom AHA 3601 ASICs. The AHA36-AHA362 boards are limited to only handling static Huffman blocks and required software to be modified to add support, The cards were not able to support the full deflate specification, meaning they could only reliably decode their own output, a stream that did not contain any dynamic Huffman type 2 blocks. Bullet point store compress 300 /MX3 from Indra Networks. This is a range of PCI-ID colon 17B4 colon 0011, or PCI-X cards featuring between 1 and 6 compression engines with claimed processing speeds of up to 3.6 gigabits, 450 megabytes per second. A version of the cards are still available with separate band web enhance specifically designed for web serving use rather than SAN or backup use. A PCIe revision, the MX4E, is also produced. Okay. AHA363-PCIe /AHA364-PCIE /AHA367-PCIE. In 2008, Comtech started producing 2 PCIe cards, PCI-ID 193F colon 0363 /193F colon 0364 with a new hardware AHA3610 encoder chip. The new chip was designed to be capable of a sustained 2.5 gbits using 2 of these 3 chips. The AHA363 PCI boards can process deflate at a rate of up to 5.0 gbits, 625 megabits, using the 2 channels, 2 compression and 2 decompression. The AHA364-PCI variant is an encode-only version of the card designed for outgoing load balancers and instead has multiple register sets to allow 32 independent virtual compression channels feeding to physical compression engines. Linux, Microsoft Windows, and OpenSolaris kernel device drivers are available for both of the new cards, along with a modified zlib system library so that dynamically linked applications can automatically use hardware support without internal modification. Scroll down here. The AHA367-PCI board, PCI-ID colon 193F colon 0367, is similar to the AHA363-PCIe, but uses 4 AHA3610 chips for a sustained compression rate of 10 gigabits per second, 1250 megabytes per second. Unlike the AHA362-PCIX, the decompression engines on the AHA363-PCIe and AHA367-PCIe boards are fully deflate compliant. Nitrox and Octeon processors from Cavium Incorporated contain high-speed hardware deflate and inflate engines compatible with both zlib and gzip, with some devices able to handle multiple simultaneous data streams. HDL deflate, GPL FPGA implementation. Intel Communications chipset 989XX series Cave Creek for the Intel Xeon E5-2600 and E5-2400 processor series Sandy Bridge-EP/EN supports hardware compression and decompression using Quick Assist technology depending on the chipset. Compression and decompression rates of 5 gigabits to 10 gigabits to 20 gigabits per second are available. Decoders/decompressors, or decoder/decompressor. Inflate is the decoding process that takes a deflate bit stream for decompression and correctly produces the original full-size data or file. Inflate-only implementations. The normal intent with an alternative inflate implementation is highly optimized decoding speed or extremely predictable RAM usage for microcontroller embedded systems. Assembly. 6502 inflate, written by Piotr, I don't know how to pronounce that, Piotr Fusik in 6502 assembly language. SAMFlate, written by Andrew Collier in Z80 assembly language with optional memory paging support for the SAM S, I don't know how to pronounce that, SAM COUPE, and E has an accent mark over it, and made available under the BSD/GPL/LGPL/DFSG licenses. Gunzip, written by Lorenz Hoist in Z80 assembly language for the MSX, licensed under BSD. Inflate.asm, a fast, efficient implementation in M68000 machine language, written by Keir Fraser and released into the public domain. Then we have C and C++. Kunzip by Michael Kahn, and unrelated to Kzip, comes with C source code under the GNU LGPL license, used in the GIMP installer. Puff.c, which is some source code I've been looking at. Zlib, a small unencumbered single file reference implementation included in the contrib/puff directory of the Zlib contribution. TINF, written by Jorgen Libson, I'm probably butchering that, in ANSI C, and comes with Zlib license. Adds about 2 kilobytes of code. TINFL.c, and then in parentheses min.iz, public domain inflate implementation, contained entirely in a single C function. That's kind of nice, one function. Okay, then we have PCDE zip, Bob Flanders and Michael Holmes, published in PC Magazine 1994-01-11. Inflate.cl by John Foderaro, self-standing Common Lisp decoder distributed with a GNU/LGPL license. Inflate.s7i/gzip.s7i, a peer-seed7 implementation of deflate and gzip decompression by Thomas MERTES, made available under the GNU LGPL license. PyFlate, a pure Python standalone deflate, gzip, and bzip2 decoder by Paul Sladen, written for research/prototyping, made available under the BSD/GPL/LGPL/DFSG licenses. Deflate Lua, a pure Lua implementation of deflate, and gzib/zlib decompression by David Manura. Inflate, a pure JavaScript implementation. Inflate, a pure JavaScript implementation of Inflate by Chris Dickinson. So I might want to look at that. Paco, a JavaScript speed optimized port of zlib, contains separate build with inflate only. I've already looked at Paco. What I really want is something that doesn't have any dependencies at all. So none of this npm install stuff, or oh, it works on node servers, but it doesn't work on the client. Alright, so let's keep reading. Hardware decoders. Serial Inflate GPU from BitSim, hardware implementation of Inflate, part of BitSim's BADGE. BitSim Accelerated Display Graphics Engine, controller offering for embedded systems. See also list of archive formats, list of file archives, compression of file archivers. And then we have some references, which I don't think time conducive to read, so I'm going to skip over the references. And some external links, which I think might be kind of valuable to read over. So I'm going to read over the external links. pkware Incorporated's appnote.txt, zip file format specification, section 10, X deflating method 8, RFC 1951, deflate compressed data format specification version 1.3, zlib homepage, an explanation of the deflate algorithm, extended application of suffix trees to data compression, an excellent algorithm to implement deflate by Jesper Larsen, zip files, a history, explanation, and implementation, walkthrough of deflate implementation. And we are pretty much at the bottom. So we have a little bit more that I'm not going to read. Data compression methods. So we just have a list of, looks like a vocabulary list of names and file extensions and acronyms. I don't think this is time conducive to read through as well. So I'm just going to slowly scroll through it all. And category, lossless compression algorithms. This page was last edited on 30 July 2020 at 14:47 UTC. Text is available under the Creative Commons Attribution and Share Alike licenses. Additional terms may apply. By using the site, you agree to the terms of use and privacy policy. Wikipedia is a registered trademark of the Wikipedia Foundation, Incorporated, a nonprofit organization. And that's it.